Hello everybody and welcome back to the discussion of operation research, lesson 20, optimization of nonlinear programming. In the previous discussions, we have seen that how to solve linear programming, and we have seen different types of linear programming like transportation problem, assignment problem, and so on. But in reality, however, there are also nonlinear relationship between the variables. So the objective of this particular lesson is finding the optimum solution for the nonlinear programming problem. A key assumption of linear programming is that all its functions, that is the objective function and the constraint functions, are linear. You see here, this is the standard form of linear programming, that is maximization of z equals c1 x1 plus c2 x2 and so on. This is objective function subject to the restriction or the constraints a11 times x1 plus a12 times x2 and so on. These are the constraints, and as you see, all the objective function plus the constraints, they have linear relationship between the variables. Linear relationship, that means the exponent of x, the exponent of the variable x is 1. So it is a linear relationship that is explained simply as y equals ax plus b. This is a linear problem, ax plus b, where the exponent of x is 1. The exponent of x is 1, so it is a linear programming. And all our previous discussions are built on this assumption. However, this assumption essentially holds for many practical problems. It frequently does not hold, because there are other practical problems having a relationship between the variables which is not linear. For example, the relationship between the variables may be quadratic or cubic, like x raised 3 cubic, or it may be what? It may be exponential relationship. So these are an examples of nonlinear programming. A nonlinear optimization problem is any optimization problem in which at least one term in the objective function or in the constraint is nonlinear. So it can be an example of quadratic equation, exponential equation, cubic equation, any polynomial equation which is out of what? Linear programming can be termed as nonlinear programming problems. Many business processes behave in nonlinear manner. That means their relationship is not linear. For example, the price of the bond is a nonlinear function of the interest rates. The price of the stock option is a nonlinear function of the price of the underlying stock. The marginal cost of production often decreases with the quantity produced, and the quantity demand for a product is usually a nonlinear function of the price, nonlinear. So this type of real problem can be treated with a nonlinear programming problem. Now let us see some important points in nonlinear programming before solving a problem or before solving an example. Let's see some of the important terms in nonlinear programming. That is local and global optima. A feasible solution is local optimum. As the name indicates, it's local, not global. Global is wider scope, whereas local is just a small scope. If no other feasible solution with a better objective function value are found in the immediate neighborhood, a solution is local optimum if it is above or if it is better solution than the other neighborhood. A point is local maximum if no other feasible solutions with larger objective function value are in the immediate neighborhood. So if it is local maximum, locally that point is that point provides the maximum objective function. So we can call local maximum, not global maximum. Nonlinear optimization problems can have multiple local optimal solutions. There may be more than two local optimal solutions, but it has only one global optimal solution. A feasible solution is global optimal if no other feasible solution with a better objective function value are found in the feasible region. So if there is no other value which can make better optimal solution, so we call this global optimum. Global optimum is the one which has the maximum objective function in the case of maximization, and which has the minimum objective function in the case of minimization. So in the case of maximization problem, the global optimum corresponds to the global maximum. For the minimization problem, a point is global minimum if no other feasible points with a strictly smaller objective function value are in the feasible regions. So this is called global minimum. This is called global minimum. So these terms are very important while we discuss about the nonlinear programming problem. And the other important concept that we encounter in the nonlinear programming is application of derivatives. So we have to have some basic skill about the application of derivative or the basic derivatives. At least we have to know about how to derive the polynomials. Nonlinear programming has the same format as linear programming model, but the objective function or the constraint or both become what? Nonlinear. By nonlinear, we mean that the relationship will be exponential, will be logarithmic, or it will be what? It will be quadratic or cubic, and so on. Most mathematical techniques for solving nonlinear problems are very complex actually, and we use derivatives just to solve some of the nonlinear programming. And thus we will use the principles of differentiation to identify the maxima and the minima. Let's take one simple example and let's solve this example. Look, the profit model is given by what? Maximum of Z equals VP minus 10,000 minus 8V. Subjected to what? Subjected to V equals 1,500 minus 24.6P, such that V is volume. V is the volume and P is the price. V is the volume, or it can be the sales volume, and P is the price. So the objective function of this model is nonlinear because here there are two variables, right? In the objective function there are two variables, that is the volume and the price. When we substitute the volume instead of the price, so we get here the quadratic equation. So it is not linear, right? The objective function is not linear, so this problem is non-linear. By substituting what? V with price into the objective function, so we get what? Instead of V, because here V is 1,500 minus 24.6P, so instead of V, we can substitute what? This value. So we get what? We get the quadratic equation of what? Objective function. It is a quadratic equation because the exponent or the power is 2, right? Here it is 2. So it is quadratic equation. Since it is a quadratic equation, so the problem is nonlinear programming. So for this nonlinear programming, we use derivative to find out the optimum solution. Using the derivative principle, since nonlinear optimization problem can have multiple local optimal solutions, we have to identify the minimum and the maximum. So before that, it is better to see some of the principles of what? The principles of derivatives. The principles of derivative. Here, look, here, if the first derivative is equated with 0, and we get what? The critical values. The critical values is obtained by the first derivative equate with 0. So these points are the neither increasing or decreasing, or it can be minima and maxima. So the minima and the maxima, or we can say the turning point like this, like this, like this. So this is a turning point, by the way. This is a turning point. This is a turning point. So, or we can say these are the maxima, these are the maxima, whereas this one, the minima. And we can get this maxima and minima by first derivative and equate with 0. Equate with 0. And if we derivate for the second times, if we derivate for the second times, and if we get less than 0, when we substitute those critical values, so if we get less than 0, if the function, the second derivative function is less than 0, so f of x is maximum at x. So f of x is maximum. And if it is greater than 0, f of x is minimum value. So we can identify the maximum and the minimum value by derivating twice, and substituting the x value, that is the critical value that we obtained in this step. So if we get the double derivative of x less than 0, so that is maximum value, f of x is maximum value at x, and if the second derivative is greater than 0, so f of x is minimum value at x. Anyway, we will see it with example. If f of double derivative equals 0 or undefined, that means maybe some number divided by 0, so that point will be inflation point. It is the point where the graph changes from convex to concave, or vice versa. By the way, here are the maximum, here are the maxima, here are the maximum point, and here is also the maximum point. Here is a maximum point, but here is a minimum point, that is a critical point, and this point and this point, this point and this point are the inflation point. It is the point where the graph changes from convex to concave, or vice versa. So these are the inflection point. This one is inflection point. Inflection point. Okay, now let's come back to our problems. Since here is the objective function, let's derive the objective function to find the critical values. When we derivate, as you know, when we derivate this number, this with respect to p, so the p will be deleted. By the way, when we derivate, let's write the formula. If we derivate x raised n, so the derivation equals what? n times x raised n minus what? 1. n minus 1. So you can use this formula. While you derive a polynomial. So in this formula, we get the first derivative, one of the objective function, that is z derivative 1696.8 minus 49.2p. And when we equate with 0, so p can be obtained like this. P is this one. When we equate, first we have to derive and we equate with 0 just to find out the critical values. So we get what? We get p equals 34.49. When we derivate for the second time, just to know whether it is maximum or minimum, so we have to derivate for the second time, that is double derivative. So when we derivate twice, this one is the first derivative. So when we derive this for the second time, so we get minus 49.2. So since minus 49.2 is less than what? Less than 0, so f of p at 34 or the z at 34 is maximum value. So it is maximum value at p equals 34.49. And when we substitute this p with the objective function, so we get what? We get p z equals 7,259.45. So this is the maximum value that we obtain with a price of what? A price of what? 34.49. Let's add one more example. Assume the following relationship for revenue and cost function. Find out what level of output X, where X is measured in tons per week. Profit is maximum. So we want to maximize our profit, and we have to find the maximum. We have to find the output that can maximize our profit. We have to find the output that can maximize our profit. So here, look, Rx equals, that means revenue equals 1000x minus 2x squared, and cost equals C of x equals x cubed minus 59x squared plus 1315x plus 5000. So the profit equation will be, Px equals revenue minus cost, cost. When we replace revenue with this and cost with this, so we get what? We get what? We get this polynomial having cubic and quadratic equation. So it's obviously this one. It is obvious this one is non-linear, right? Non-linear. So if it is non-linear, so we have to solve this with differentiation. Let's derive this. Profit equation, and when we derive it, we get what? We get quadratic equation. Now let's find the solution for this quadratic equation by what? By quadratic equation formula. Do you remember quadratic equation formula? Minus b plus or minus under radical b square minus 4ac over 2a. I think this is a quadratic equation. Anyway, this is a formula. Anyway, you can check it. I may made a mistake. Maybe I'm not sure. Anyway, you can use this quadratic equation after checking whether it is right or not. So using this quadratic equation, we can get what? X 3 and x equals 35. These are the critical values. And the second step should be, we have to find out whether these values are maximum or minimum. We have to find out whether these values are maximum or minimum. So to find out that, we have to second derivative of this quadratic equation. When we derive for the second time, we get minus 6x plus 140. So when we substitute 3 into this equation, so we get what? We get 94, which is greater than 0. So P of x at 3. P of x at 3 is minimum. But what we need is maximum profit, right? So we ignore this one, right? And P of double derivative of 35 equals minus 96, which is less than 0. So P of x is maximum at 35, at x 35. So at the output of 35, our profit will be maximum. At the output of x, that is 35 tons per week. So we can get the profit. We can get the P of X, we can get the P of X by just substituting 35 into this equation, so we can get the maximum profit. That is, we can replace here minus x cubed plus, here it is 57x square minus 315x minus 5,000. So you can replace this, you can replace 35 into this equation so as to get the profit. But our question is just to find out the output value that can maximize our profit. That is 35. That's 35. Here is the answer, right? This value makes our profit to be maximum. Thank you for listening, and hopefully we will meet with the next lesson. Till then, have a good time. Bye.